Good morning. I am Ken Bullock, the director of the Center for Fundamental Physics at IAS. Before we start today's lecture, so let me introduce our speaker today, Professor George SMOOT. George actually did his PhD in experimental particle physics at MIT. And got his PhD in 1971. And then after that, he moved to Berkeley as a postdoc, and then eventually became the senior staff scientist of Lawrence Berkeley National Laboratory, and also joined the physics faculty at UC Berkeley. He has spent most of his career at Berkeley. However, he also has spent some time in Hong Kong, and now he is the professor at large emeritus of IAS. Now, even though he was trained in experimental particle physics, but after he moved to Berkeley, actually he switched to studying cosmology. And in the beginning, he teamed up with one of the Berkeley Nobel laureate professor, Alvarez, looking for the antimatter in the upper atmosphere of the Earth. But then later on, he realized the importance of cosmic wave, microwave background, and then he spent time doing that. And in 1992. The Kobe team that Professor SMOOT led discovered the very small variation in temperatures in the cosmic wave, microwave background, and this is very important because this is a crucial condition for the formation of galaxies in the universe, and because of this discovery, Professor SMOOT received the Nobel Prize in 1992, I think.
No, 2006.
Yes, yeah, because you announced it in 92. Because I was thinking,
right, 92 was all the noise.
Exactly, yeah, right, okay, yeah. Now, besides cosmology, actually, George is also very interested in other areas. For instance, he has interest in artificial intelligence. And also, you can hear a little bit later on today, and also in medical sciences. Now, besides the Nobel Prize, George also received many honors and awards. For instance, he received the award from NASA, and also the Ernest Lawrence Medal from the Department of Energy. As well as the Einstein medal. So today now he is going to tell us about his work in stem cell research. So let us welcome Professor SMOOT.
Thank you, Ken. Ken, you didn't mention that we used to have our offices across the hall from each other. And often we were teaching different sections of the same course. And I would teach his course when he had to go to town, and he would teach my course. The university still complained at us for that kind of thing. So it's my pleasure to give a talk here, finally to give this talk. This is not your usual Nobel laureate lecture. This is a lecture that's different, but I'll see it. And I've been calling it in my mind my ring lectures. That I should be giving a set of 4 lectures, just like Wagner's, operatic or drama series, The Ring. I haven't figured out how to give the last one, but I can tell you what the third one should be because I started working on it. And the first one I gave on Friday, and the point I was trying to have there is because of tremendous advances in technology and future promised advances in technology, and that we've actually entered the area that John von Neumann named the singularity. It's actually started, and that's a time in which new technology discoveries come so quickly that human beings cannot respond to them. But more importantly, those new discoveries and technologies are at variance with human institutions and laws and so forth. And those will be swept away, and they'll be swept away pretty soon. Usually it takes like a recession or depression to start sweeping things away quickly. We have people working to disturb the world order. But those discoveries, if we kept the world order together, in 5 years would make us twice as wealthy as we are now. So it's in everyone's interest to try and keep the world order together, but to also adapt. And so one of the things, since I was talking to professors at this meeting, I didn't mention one of the human institutions that will be swept away is the university. Okay? Because professors don't want to hear that, because I know I was worried that online instruction was going to affect teaching when I was young. Now, the teaching load was kind of hard in another sense. It's clear that a lot of undergraduate courses should already be taught. But the fact is, it was the reason they justified paying our salaries, why the state gave money to the university. Same thing is going to happen here. And the university has to reinvent themselves by doing projects that you can't get with the other technology. So this is the example of a project that we can do, as the University HKUST, that justifies continuing to get government money when the money is going to be cut back to all the other universities. There's going to be one university left in Hong Kong in 10 years. It's kind of time scale. So that's just to get you, to get your attention and get you concerned about it, because this is one of there are 3 projects I can think of. This is one of the ones that the government and the population and the people in the university are all going to say is a good thing, right? Because it's going to provide for them much better health. It was not a medical thing. Medical is when things get broken. Health is when you're not sick and when you're living well and you're having a nice time and you feel good. Right? That's the thing that you want to do. So you want to be working towards the thing where you have health right until you have the problem where you have, disease. Right? That's another thing. And so stem cell is the thing in the right direction. And Canview didn't mention it because he doesn't remember. 50 years ago, I started an effort where I applied physics against cancer. Okay, so the word "against" is very important because just before, a few years before that, I had to take college entrance exam, and one of the things we had to do was correct a essay to prove you could read and write. Okay, and the title of the thing was "Crusade for Cancer." Okay, well, we're not crusading for cancer; we're crusading not to have cancer. And so, I'll mention one of the things that moved me into the stem cell business as the correct way to deal with cancer. All right, so here we're going. This is the background. The only thing wrong with this background is there are people in it besides the patient. It really should be computers and machines doing 99% of stuff, and the patients, the handlers of the patient are probably nurse practitioners. You'll see something about that. So you can say all these good things about the future healthcare, where we should have a school of futuristic advanced healthcare and some medicine here as what the university is actually doing. All right? And healthcare is going through a tremendous revolution due to the fact that when I was young, digital won out over analog. You might not know that, but when I was in college, my roommate worked part-time at Draper Lab building analog computers to train the astronauts how to land on the moon, because the digital computers were not good enough and fast enough. But analog computers could be made to do that, so that learning to actually land, landing is not so simple when there's craters and boulders and stuff. And they had to train the astronauts how to do that, and they used analog computers those days. It wasn't much longer after that that digital computers took it over and we started digitizing everything. Okay? So we've got a lot of anti-aging and healthful longevity, personalized healthcare stuff. We'll come back to that hopefully in my next lecture. We have cellular genetic treatments. We have a deep understanding of cell functions and growth signals between cells, something that I actually knew about indirectly when I was younger, but now understand in a much different way. We got CRISPR, Cas9 technologies so that we can do genetic interventions easily and cheaply, right? And there are more than 5,000 gene therapy trials listed by the National Institute of Health. There's only 1,000 diseases, so, you know, we're overkill here, except there's different modulations, so it's maybe not. And there are more than 8,000 worldwide, and I'll show you some stuff. And we got robotic surgeons and robotic doctors and medical image readers, of which 2 out of the 3 have already kind of taken over the field, right? But the third one, the doctors are resisting. Okay, so here's a slide that I was giving in talks some years ago. And this is a sort of a talk to say, when your baby is born, you take the umbilical stem cells and you store them. And why is that? Well, because those are as close as you can get to the pluripotent original stem cell. And you can, in principle, preserve them and take care of them so that 50 years later, when there's something in you that needs fixing because you have something, you can go in there with those stem cells and fix it. Now, we've made a lot of progress in recent years so we can take some adult cells that are not so advanced, that are quasi-stem cells, and you can try and use those to do that. That's how the 5,000 treatments are going on. And this is just shows the concepts there. And I gave talks a couple places, and 2 countries decided to do this. One of them you can guess, it's Singapore. The other one was Hungary. Recently, Hungary has quit doing this for whatever reason, but that's the only 2. And this is an advertisement that I found 3 or 4 years later from a company in Hong Kong advertising how they will come to the hospital, get your baby's stem cell, you know, take it to the stem cell treatment center where it gets all fixed up and put in the the ether bags, and then put in the thing. Now that was fairly primitive, but this is what you can do. And a number of people did that. And one of my colleagues, we'll come back to later, I convinced to do that. His son is now almost 18. He took it. Now there was an issue of what happened, and we'll get back to. Okay, so this is also a moderately old slide, 10 years old slide that I put in. That's why it's got some Chinese in it, because I gave it. It's a Chinese company. How many diseases are treated by stem cells? Well, in 1988, it was 1, right? By 2007, it was 40. By 2017, it was 80. What's it going to be in 2 years? The answer is a lot, right? And so that's unfortunate for most of the people in this room because they haven't got their blood stem cells. They've got to get their quasi-stem cells from other things, and we'll talk about what that is. Okay, so here's one of the things that I could find, but it's only good out to the year 2012 plus 1, right? That is the number of stem cell clinical trials going on as a function of year. What you can see is the exponential growth, and then is it rolling off the top or not rolling off at the top? That's because it was done in 2012, so you don't get the full degree of what's going on. And there's a whole bunch of stuff. There's a nice set of guys, mesenchymal stem cells, right? Usually when they're talking about that, they're talking about stuff taken from your bone marrow, right? But there are other ways to get these kind of things. So not only can you get your umbilical stem cells if your parents were foresighted, you can do it now as a person. And there's another thing you can do, which was something that I got involved in, and then later Nora and I got involved in, which we'll get to, but I want to go through this. Okay, so here's a more up-to-date version, right? It supposedly goes to 2025, and it shows that there are stem cell activities going on. You'll see, I'll show you the next slide, mostly in North America and in Europe, but somewhat in Canada. I mean, not in Canada, in China. And you can look at the various kinds of things they're doing. They're doing stem cell treatments for eyes. There are 4 different stem cell treatments for eyes that I know about. I'm looking at one of them. It's for macular degeneration. I may be getting that in this eye. I have to wait and see. That there's dry eye and so forth. But the age one is one that happens, unfortunately, when you get older. So there's a lot of different kind of things that you can look at and see. And there's a hint that it's rolling off, that we're not having the exponential growth in stem cell trials that we had, 4 or 5 years ago. But that's a sign that they're transitioning into this next level. And has anybody in this room had a stem cell treatment? It's funny, now when I run into people where I was doing other stuff, I've found already 4 people who had stem cell treatments, and one of them for knees that was miraculous, for somebody who was originally playing tennis and then went to pickleball and so forth. They had a wrist issue and knees issue. Okay, so here's the global stem cell market forecast. Now it depends on what you're talking about it by therapy. It's $19 billion last year, predicted to be $54 billion way out in 2033, which is 8 years away or something. It's still exponentially growing, and it's growing at a rate that's in the 27 to 28% per year. This is really fast, okay? It's hard for people to try and understand what's going on. All right. Now here's another ad from Hong Kong. I took this off their website page. Do you notice anything here? Well, a lot of it's about making your face look young. But there is stem cell storage, and there are some other treatments, but mostly it's about making people look young. That tells you what's important. But Hong Kong has got the oldest population in the world. It's made some mistakes in its, well, I think it was immigration other program, and a lot of people immigrated as opposed to immigrated, and there's a severe aging issue, but people still like to look nice, and a lot of people in Hong Kong are rich enough to afford this. And this is one I picked from a place in Mexico, and you explain why. There's 3 different places that I look at this and stuff. This is an ad that they think people will respond to. That is, better hair. Well, that's kind of like a better face, but not as obvious. Improved vision. That is something, eye aging is a very serious issue, especially if you have an aging population. So your immune system, well, this is good. This is different. Metabolism, right? Well, that's related to the immune system, what the immune system most. And you look at these things that they're advertising that they will give you stem cell treatments for. Right? And so these are not just fly-by-night places. These are people that are running real stem cell organizations treatments. And, they even tell you what they're going to do. They're going to do a consultation. They'll schedule treatment. And in some cases, if you're busy and rich and you can't afford to go there, they will take the stem cell samples from you, fly that to their factory, produce the stem cell treatment for you. 21 days later or something, you come down, check into a first-class hotel, get a check to make sure that you're not got an infection or some other kind of thing like that. Then you get injected, and you're watched for a couple of days, and then you go home. That's it. No surgery, no anything. You just get that treatment. Well, that's kind of okay. It's not the best, but it's okay. Okay, and here's another ad advertising the 10 benefits of cell therapy in Mexico, right? Well, they got a bunch of rich customers just north of the border, and they're not a bad place to go visit and so forth. And so they have allogenic mesenchymal certified cells and so forth. You get it from you, but they're going to give you the stem cell treatments. And while we were down there, we were just down there recently, a place opened up in what I consider a medium-sized town with a suite of doctors that were giving stem cell treatments. Right? It's for the tourists and the locals. All right, so what's the level of the market? And the reason I'm doing this is because this is going to be a joint progress between the university, private people going to make a lot of money, and the government who wants to provide health care to the people, right? And if you look, 2 years ago, it was 20 million. They're predicting that in 5 years, it will be, I don't know, I can't read it, 113 million or something like that. That's not very impressive, except it's in a country that a lot of people in the U.S. considered backwards, and yet when you look at these facilities, they're quite amazing. Get back to what's going on. So there are a number of countries vying to be the low-cost stem cell provider. When you have a field that's growing exponentially, anybody that starts a business in that will make money. After you reach a certain level, it turns out it's the low-cost, high-quality producers that have a great reputation that eventually take over. Some of you may not remember the way I do, but I can remember when personal computers started up like crazy. Some of you may remember this. And there were companies all over the place. And you never hear about Eagle Computer anymore. I remember that particular one because on the night they went public, one of the co-founders drove his Ferrari into a telephone pole at high speed, and that wasn't good, right? But Dell Computer, Apple Computer, IBM, IBM has kind of been faltering some. It was by far the biggest. There's only like 4 computer companies really left that in the U.S. There's some more in other places in the world. But the number of computer companies crashed down because there were certain people who could provide a quality commoditized thing that everybody bought and used, right? And so you can see how the price depends on how much people think they're willing to pay, right? Because they got to, compared to the U.S., where it costs $20,000 to $50,000 for such a treatment, here you're looking at stuff that's running between, $1,500 and $5,000, depending, unless it's some kind of special disease like the hematopoietic stem cell therapy. That depends on what they think they can get out of the person. And there are a couple of other countries that are trying to do stuff in this, like Malaysia, but they're in Colombia, but they're not going to be big players in this market because they haven't got up the curve yet, I think. It requires some brilliant, very rich businessmen to come in and pull them up in the state. But it's just an example of the kind of stuff that's actually going on now, and it's surprising nobody in here and nobody knows anybody who's gotten stem cell treatments because it's starting to happen quite a lot around the world. Okay, so here's Thailand, and I'll mention Thailand because I'm working with a group to open and we thought we were going to do very well, but then Chinese New Year came and slowed everything down, and then there's another issue, which is that they want to have it at the Royal Thai Hospital, and I wanted it to be in the Karst Mountains for reasons you'll see later, and just for 2 reasons, and one of which was to get it away from the doctors. So the doctors didn't intervene in the middle. They only took the samples and gave it away, and nurses took the samples, and so we can see. But you can see Thailand is growing, and it's looking towards $500 million by 0.6 billion by 2030. Exponential growth, right? That's what phases we're in. Okay. Well, what about China? I think this is China. Okay. Look at this. Already, it was $1 billion last year. We think by 2030, it will be approaching $5 billion. Okay. That's serious money. That means there are serious players trying to figure out how to get in this market and do things. And I'm just trying to convince you that the people who want to make money want to be in this business, right? Because they can see it's something that's really the future. Okay, and worldwide, 27 billion. Okay, because already in the United States and Europe, there are people doing medical tourism or getting treatments in those countries. Okay, and so here's the geographic location of the clinical trials. right? You can see there's a bunch in the U.S., and you know why some are here. There's certain places that are high biotech areas that have good hospitals and medical stuff, and high-tech industries. They have the base in which to be able to do that. You say that again here in Massachusetts, in Maryland. You look at it and see. And again in Europe, there's a whole lot here because it was a big pharmaceutical and big mouth. And again, France doesn't want to be left behind. Surprisingly, Spain is coming up very big in this. So those are very serious areas. There will be that kind of activity here, but not so much in clinical trials, in actual treatments. There will still need to be some advances in the field. It's very early. It's like renewable energies. It's developed some, but compared to the internal combustion engine or drilling for oil, mining coal, those are really old technologies. We're talking about a new generation here. There will be a new discovery. That's what universities can help with in a great way. Okay, don't forget your mitochondria. Turns out your mitochondria are responsible for somewhere around 45% of the effects of old aging. That's because you mistreated your mitochondria like I did, and I had a Diet Coke, a non-Diet Coke this morning, just to give me a little punch to be able to talk to you. You know, a big shot of sugar makes your mitochondria work extra hard. If you overtrain, your mitochondria work extra hard. If you don't train enough, your mitochondria don't get really nice. There's a narrow line to walk. You already knew this. Moderate exercise, good diet, all those things, they have, they're there for a reason. They're the things that make you be healthier and keep your cells working better. Because, well, we'll talk about it, your cells can only divide so many times. There's the telomere issues, and it is for these guys too. And there's issues of what's called a Hayflick limit, which is every time a cell divides on general, it gets one genetic defect. And you can't have too many genetic defects before you have a problem. But look at this. Look at what these things are. Osteoarthritis, osteoporosis, molecular, it's me drinking Cokes. Why I got, aged macular degeneration, COPD, osteosclerosis, right? Diabetes. Whoa, I shouldn't have had a Coke either. But anyway, your mitochondria there, now pay attention to them, because when I talk to you later, mitochondria in your human cell, your nucleus occupies some percent. The mitochondria occupy up to 3 times that. And that becomes important when you start beating up your cells for various reasons. And we'll see. Okay, so here's one that I picked because I happen to know 2 people that I've discussed with who have spinal cord issues, one in the upper back where it was fusing, and one in the lower back when it was in an accident, and it cracked and broke the nerves, right? And has to walk around with braces or a roller or whatever it's like that. The fact is, you can treat that now. You can take some pluripotent stem cells and make them into spinal cord nerve cells and inject them into the right places. Now, this is a site that should send shivers into you. Here are all the little pieces where they're growing, the little stem cells in order to reproduce them. Why are they out in the open? Okay, this should be a completely automated thing with closed system, as I'll tell you later, closed system where the human beings who are working on it and the machines that are making it, they're completely sealed from each other, so the person's not exposed and the stem cells are not exposed. But this is actually, it's a fixed up picture from an actual lab where people are doing this. It's very crude state in its stages these days doing this kind of statement. But just like there are 4, actually +2, eye treatments with stem cells, it's the pre-stem cell ones and so forth. There are a number of treatments for spinal cord issues, right? Spinal cord and vertebrae issues. And, it's nice to have the pictures there and everything, but they shouldn't It shouldn't be like this. It should be an automated system. Okay, so let's look more at the process, because in the end, it is the process that you want to improve and make it safer and make it automated and reliable and cheap. That's we're making a product that we're going to give to 10 million people here in this set of islands. We want it to work well and be safe, okay? So there's the first thing here. So this is one of the returns to using physics. There, I did several stints. We're using physics to cure cancer. I became convinced that the CAR T-cell approach is by far the best approach. And people that don't know what it is, you take your white blood cells, your lymphocytes, and you take them away out of your blood, and you save them to when you need them, and then you activate them. That's what the CAR is, cancer, sensitivity to the particular cancer. So you have to give it the cell some information about the cancer, and then grow a whole bunch of those cells and inject 1 million of them back into the patient, and it eats the cancers. And even the ones that have metastasized off to the side, that's why they cut such a big hole in me, because they want to get any ones that are turned away. They way cut bigger than the skin cancer I had. They wanted to make sure the metastasized cells didn't get left behind, and they didn't want to go through the sort of the advanced procedures some places in the U.S. do, where they grind up a little bit and make another cut, grind up a little bit and see till they run out of cells that look like they're cancerous. But anyway, so the goal is to get your T cells, the immune system cells, and preserve them for the 20% chance you're going to get cancer. Now, if you're older like me, your odds go up because most of the cancers goes the 6th power of your age. So, and there's reason for that, but that's the next talk or something. The thing is, you want to store them and save them. When you get cancer, and the 20% chance you would if you gave your stem cells what you should have, which was in your late 20s, early 30s, as opposed to the umbilical ones, because it's got to learn about what things it should be, attacking and not attacking. And then you unthaw them, and you select ones, and you activate them to have a gene that attacks the particular cancer you have. And then you do cell expansion. That is, you divide those cells in two a whole bunch of times until you get up to 1 million cells. And then you preserve some of those for the second treatment, and the rest goes into the patient. Right? That's a simplified version of the workflow. Right? And it's not a perfect process because there are humans and stuff involved in partly, but a lot of it is partly automated and so forth. Let's look at it a little more carefully. If we think about why this problem is the problem it is, okay, there's a huge amount of computer power and data handling and stuff. And if I get my third talk finished in the ring thing, there's going to be way more math and AI involved in it, because you're going to already have the person's DNA. If it's their umbilical DNA, you can map that completely if you have the right tools. We're not quite there yet, but they're going to get there. And you can then make predictions of what things that person should be looking out for in their life and track them and see if they're going to do that. Because in fact, there's a huge amount of things that are stochastic and environmental and so forth. And by tracking the person, you can make a prediction of which things they're likely to have problems with, be monitoring them from that, and be ready to take their stem cells and make a fix. You could see that 20 years from now, we can actually make whole organs and so forth, but that's a more complicated kind of thing. But that's a tremendous amount of stuff. If we're going to handle something on the scale of Hong Kong, you're going to want to handle on the scale of millions of stem cell batches or T cell batches, and you have to track that data. You have to track the DNA. You have to do a huge amount of stuff. It's a huge data program, but if you can cross-link data, you can learn a lot more if you can follow whole cohorts. And it's a longer-term view of what's happening. So there's a whole bunch of things that you want to do, but I mean, this drawing is kind of a simple drawing. It's going to require very huge data center and operations to monitor the quality and what's going on in the whole storage and the processing, but also to make models of the person and seeing what's going to happen, what their reaction should be, what's going to be going on. So, but that's the next lecture. Okay? So here's the CAR T-cell stuff that I got in about a decade ago. Is convinced that the other approaches that I had were not as good as this. And even though this isn't physics directly, there's physics indirect. So I got involved in consulting with Shanghai Cell to help design them a highly reliable liquid nitrogen cooling system, so that if a typhoon came or power outage came or whatever, they would still preserve all the cells and keep track and have a way to keep track of everything. Okay, what you do, you do what they call leukapheresis. You get the blood, you separate out the T cells, you go through and select the ones you think that are good, right? And then you either freeze them and store them, or you modify them to genetically attack the particular kind of cancer that's going on. You expand them quite a lot, you put them back in the patient, and it eats their cancer, right? And to my surprise, one of the things that I had the surgery for was that I had a fairly aggressive skin cancer. The clinical trials now for taking care of that skin cancer by using the CAR T cells is much more successful than cutting, like they did cutting the top of my ear off. It's, you don't want melanoma, so it's good to cut it off, but it's actually crude compared to having your own immune system eat the cancer cells. And so that's why I'm convinced this is the right kind of thing to go. And I gave my blood to Shanghai as part of the deal. I gave my blood to Shanghai Cell 10 years ago, and they got it stored, and we'll see what's happened. All right, and women get it too, right? It's different ways. This is a different one. This is one of the things that I had done earlier to use physics to combat it, and that was to use magnetic nanoparticles of the correct size, because it turns out cancer tumors, blood cells are all kind of messed up and strong. If you get above the regular size, it can go, if you get to a certain size, it can't go through the tumor. The magnetic nanoparticles, if you coat them, can't go through the tumor. They can go through normal vessels. So they collect in the tumors. So if you do magnetic resonance imaging, the tumors stand out like crazy. But if you also do that, you can use magnetic heating. That is, you can magnetic field flux, heat the nanoparticles. They're coated in a plastic. That plastic can also contain, chemicals to kill cancers, and you release it into cancer. The important part is concentrated. And then there are some people who went on and said, okay, if we can do that, we just burn them. If we can collect enough of these magnetic nanoparticles together, we'll just use the magnetic field pumping, and we'll burn the cancer. Well, that's crude, but it's the earlier you take the cancer and the earlier you treat it, the more likely the patient is to survive. So anyway, we'll see. So the nanoparticles came back as a way to drag them through the tumors, get some of the biomarkers of the tumors, and then put it on the T cell and train the T cell to attack that. It's funny, this is one of the techniques that works. So it's like old home week or something in a certain sense. Okay, so let's look at the whole process a little more carefully. This is still so you get the first collection of the sample from the person, whichever way you do it. And then you pack it into an insulated container, cold, and you ship it to the center where you're going to process it. You do the processing, you select out the kind of cells you need to have, and then you freeze the hell out of them. And you freeze them to liquid nitrogen temperature or liquid argon temperature, where liquid nitrogen is cheap and much faster and so on. And then when you need them, you bring them out and you warm them up, and you have to have certain survival. we're going to have to look at every one of these steps and evaluate it, and I have been trying to do that. And then you start doing the various things, including how do you make them attack the right kind of thing. It's not just cancer tumors, you can make them attack other things. And you do what they call the ex vivo expansion, that is outside of the person, but inside of a certain chamber. You grow those, force grow those cells till you got 1 billion of them, or however many you particularly need, and you take that, and here in this case you remove the beads. You harvest the cells, right? You make the dose and you cryopreserve some, and you do the testing, and then you fly it to the patient and you inject it, right? That's right. And the doctor or the nurse should be involved there, and a nurse or a doctor should be involved there. There shouldn't be humans in this part of the loop, or just in a very mild kind of way. And this is the actual cell therapy product line, and there should be in parallel DNA mapping, health protective systems, and what in engineering they call a digital twin. And medicine is just beginning to make digital twins of stuff. But there should be a digital twin of you that you can run simulations on, and those simulations tell you the consequences of your life choices, right, in terms of what's going on. That's lecture number 3, if I can get it written. Okay. All right. So here's something that I did many years ago. I made up an error budget, and it was an error budget to say, if I want to measure signal from the birth of the universe, how accurately did I have to do it? How well did I have to make the detectors? How many switches and reveals and things I do? And there was a bunch of stuff like that. And for the satellite, I had one person whose job full-time was called systems engineer. His job was to keep track of the error budget, to make sure that none of our parts and none of our things reveal that we had systematic errors that we couldn't remove. Right? Now it's very hard. So I looked at what the current rate is for good systems. That is, how bad is the stuff incoming? Well, it turns out people don't handle those samples as well as they should. It's a 40% casualty rate to the cells going in. I think that should be around 2%, but we'll see. I think of ways to do that, but we'll see. There's a storage rate, and the thing that I seem to be the only person doing this kind of stuff is noticed there is radiation, and radiation whacks storage stuff way more than you would think it would, because it's frozen and it can't fix itself. It's frozen. Okay, and then I wanted to get down to 1%. We can't do that yet, but I can give you paths which may get to that eventually. Nora and I have an invention for one half of the thing, which is the removal and unfreezing error rate, which is around 2%, right? Because you've also got to make sure that you don't put somebody's cells in the wrong place. That you can't, somebody doesn't drop it off of the 15th tier and smash it, right? There's a bunch of stuff you have to do to make sure of that. And you have to have an inspection. You can have an inspection error rate. Once you get to a low enough rate of errors and other stuff, the inspection error rate doesn't matter as much because you have fewer bad cells to have to deal with. And activated cell expansion, the error rate is high. You've got to go through and throw away 3/4 of the cells before you have a set that you can give back to a patient. That's really pretty terrible. The total loss of cells is almost 100%. It's not quite, because people are getting stem cell therapy, but there's a whole lot of intervention that has to be done, whereas I think it should be on the scale of 8%. That would mean you have less expansion to do because you had more cells to start with, and more are going to survive, and so you're going to do that. And that's the goal, that 5 years from now you want to be doing this kind of thing. And there are some things that block it, some things that don't. So I call this an error budget table because that's what we used to call it back in the antique days when I was thinking, how can we be sure we can make this measurement? Here, it's how can we be sure we can actually produce cells safely and reliable in an automated way. So I keep forgetting to use the right thing. Okay, so here's an example of expansion of human pluripotent cells. Okay, so you picked out the ones that you want to culture. You've modified their genetic or their markers, and then you put them into a medium which causes them to grow and divide fast, roughly once a day. Okay, and so what happens? Every time a cell divides, it gets an error on average. Not every one, it's Poisson kind of distribution. But you will find that if you're going to divide them 20 times, there's going to be a number of errors in that kind of stuff. You need them because if you might be going to die from the cancer, you'd prefer to have some bad cells than to have the cancer or whatever. What happens is, if it gets a mutation that makes the cell grow faster in the culture, you'll get a lot more of those cells. It's simple math, right? It's, kind of going. So when you have an extended culture, you end up with a few of the cells that are pretty much like the original, and a lot of cells that grow faster or have some other kinds of things. But some of them are going to die because their mutations were bad. Right? So you need to figure out, how can I make that a more stable situation? There's probably not much we can do. The Hayflick limit's been around for a long time. Nature has a lot of tricks and things to do. So when you're in vivo, like in our bodies, a lot of those errors get fixed. But when you're or edited or put into apostiosis or some kind of things happen, here you're growing them really fast and you're going to sort them and inject them into people. So you want to find a good way to try and handle that. Okay, so if you're looking up to 25 divisions, you're going to have some problems. You've got to figure out how to handle that in an efficient, an effective way. And you're going to want to look at them and see, genetically sample some of them to see if they're doing okay. And also realize their telomeres have probably gotten shortened here. That these are T cells, but they're not brand new T cells. They're slightly used T cells. But they're going to help you out of your problem. Okay, so here's how you store stuff. Okay, what's wrong with this picture? People are in it, right? That's the mistake. And they got a rolling cart, but they should be super clean. Her hair shouldn't be out like that. It's a lot of other stuff. But this is a real picture. I mean, I have some other pictures that I took, like a Shanghai cell and in Bohai, and Bohai cell has some stuff in it. And there are rows like this of these things that contain frozen cells, right? They're all liquid nitrogen. If you look, they're gravity fed. There's lots of things that people do semi-standard now. But you also going to want to have in your stem cell factory, when the stem cell is taken out by a machine and put into the right place, you take out a sample and that factory goes to work on it and makes it. Right now, you have humans intervening at various steps to try and check stuff. That's a mistake, right? And here's another example of a bioarchive and so forth. But when you start thinking about this, this is a pretty big deal. Right? So here's an ad. So the ones on the right are for the ad. The ones on the left are one of their competitors from higher company. Okay, so what is going on here? This one is a relatively small one, like that high. It's a big liquid nitrogen cool tank with a nitrogen atmosphere in it. There are lots of stem cell samples in each of these columns, and you can send a command by computer. It rotates around and raises the stack up so the robot arm could reach in and take the stem cell and take it over to the factory. Right? That's what's going on. This is the beginning of what it's going to take to make an automated stem cell factory. Okay. Now here's my first attempt using AI to make a picture of the thing I envisioned based on what I calculated. And I wrote this words, and I used the AI, and it sent me back this picture. And I'm frustrated with it. I'll show you a couple more that I've done. But this is just a little one, but it shows you the beginnings of the scale of what you have to be having. The one I have at the end that I made with DALI actually shows the right scale roughly, but it's got a bunch of other things wrong. Okay, so now I was sitting up in my office upstairs, and I'm looking out thinking, I want the stem cell center buried in the mountain below me, which for reasons that I'll tell you, and I want to have a power line coming in, and I want solar panels, and I want 2 liquid nitrogen factories that are taking nitrogen out of the air, a couple of other things out of the air, and putting it into 2 separate tanks that are level down below. And then I want all these things. And I described it all. And this is the picture it gave me. So imagine this is from the view out from the left here, except they put a bunch of student dorms and stuff right there. And here's another one where I tried to say it's okay. And it put plants there. It's got to be sterile. It's got to be clean. But it doesn't have to be outside. These guys should be inside shielded, not outside like this. Right? And then finally, this is one I did with DALI. And it got some stuff right. It doesn't have any solar panels. It doesn't have the liquid nitrogen stuff on the top. But it shows you the kind of scale where I want tanks like that are storing on the scale of thousands to tens of thousands of samples, stem cell samples frozen. And then I need to be able to access them robotically, and then I need to be able to do that. And over time, things are going to change. I need to be able to get in here and take pieces out and put new ones in and so forth without disturbing the whole system. I need a system to do it. Now, this is, trucks and stuff like that. You can see this is the scale of the kind of thing you have to think about, because if you really want to do all 10 million people, you need 1,000 of those tanks, right? Plus you need the factories. This is what you want to get to eventually. All right. So this is my weak AI attempt, because AI is trained to make things like other images that it sees, not like what you're telling it. Okay. So back to the science at hand. I should be checking my time to see what's going on. Here is an idea what kind of cells are in your body. So this one in the middle is how many cells you have by number. A lot of what you have is blood cells. So it's not surprising that a lot of stuff is done with blood cells. Now, one thing that isn't shown here, there are 4 times as many cells that are red blood cells without nucleus. Okay, so you don't show them on this chart, but everything else you do, right? Then there's nucleated red blood cells, which you don't usually pay attention to. But there's a whole bunch of different kinds of white blood cells. And when I first started looking at this years ago, they didn't know what NK cells were. Well, NK is short for natural killer cells. There's some part of the cell, the immune system cells in here, that are just naturally kill things it doesn't know about, right? Sometimes it attacks you, but mostly it's the thing that attacks your cancers or other things that some people have very well, and it lasts pretty well. So if you look on this plot, cell mass versus number, it goes down as almost the first power, right? What's that telling you? There's roughly equal mass of every scale size of cells, right? Which is kind of funny. Why is that power law? I haven't figured that out, but I'm sure there's a reason why the body does that. But in terms of total mass, a lot of your mass is in your bones. No surprise, you know this, right? But I'm not sure, it's a structural issue as opposed to a cellular machine functioning issue in terms of what's going on. And there are lots of different kinds of cells. And so the relevant question here is, what's the size of a typical human cell that we want to deal with? Okay, so here's the micrograph that shows HIV, it's a virus, a T cell, typical size of a T cell, and a bacteria. Bacteria is about 1 micron. This is on the scale of 7 microns. Well, I usually use a round number of 10, but it depends on what you're doing. And HIV is 1/10 of a micron. It's very small. But you look up there and you can see the different kinds of ones, and they run from 7 microns up to 18 microns. There's typical kind of scale size for the things we're going to be dealing with. Okay, except there's one special kind of cell, which is human eggs. So here's the human egg. Now, this one doesn't show it. That one kind of shows it. There are mitochondria and there's single-strand DNA. Now, single-strand DNA is very vulnerable to disruption by radioactivity. So if you're going to do it, it's better to put a fertilized embryo if you're going to do storage, right? And because you have double strand, and it's only neutrons that really consistently break double strands and ruin the stuff. But if you take an egg like this, it's big, it's 120 microns. That means its chance of being hit by radiation is roughly 100 times that of an ordinary T cell or a bunch of other of the stem cells. And it will do a lot of damage to the nucleus, and it will do significant damage to the mitochondria. So they should be stored in very low reactivity place. That's one of the things that I realized when I was doing it, which was we're getting to the cell. So apparently I'm one of the few people that realized that frozen cells and in vivo cells react very differently to radiation damage. And so storing cells, and this goes back to, I'm not sure it came Buford's, that I remember Buford Price was looking at high charged cosmic rays and thought he found stuff. But what he was using was large sheets of plastic, which are good insulators, just like completely frozen minus 190. The electrons don't move around very much. That's why they can stay preserved. Well, electrons don't move. So when you have ionizing radiation come through, the electrons just wander off and they don't come back. And you have the broken thing going until you thaw them out. And so there's an issue. And so if you do the order of magnitude calculation, there's roughly 1 muon per 60 seconds per square centimeter. So like that. Or I forgot how many, 10 through your hand in a minute or something. I forgot what it was. We used to know this by heart in the old days. I used to wear a radiation monitor, 2 radiation monitors, ionizing one and a film one. And you multiply that up to the number of square meters, a 10 to the 4th, you get 100 muons per second going through a square meter. One of these things is 10 microns on a side, approximately. So in a year, you're going to get, on the scale of 1 hit, every cell is going to get hit by a cosmic ray muon every year. You want to store it for 10 years or 100 years? Because health has gotten so good that the umbilical stem cell sorts are not needed until you're 100 years old. It's an issue, right? That's why I have 100 up there, because you have so many. So because of the lack of diffusion, because of other things, the damage to frozen cells, I calculate, should be significantly worse. And I do it several different ways, but we'll do that. And because of that, I started looking up all the background radiation doses, just to be able to show you. The cosmic rays are about 1/3 of a millisievert per year. Now there's RIMS and there's, unfortunately, in radiation there's many different. There's becquerels, which is the number of decays per second. There's the number of hits per second. There's the number of, and so on. Sieverts are weighted by biological damage. And this is done from the old days when they were worried about radiation effects on humans, live humans, right? The cosmogenic ones, we'll skip over that, but there's some stuff produced in the atmosphere by the cosmic rays that you end up breathing in and do it. So we're here on a mountain. We're getting exposed to about 0.2, perhaps a little more. Well, we get a little more cosmic rays just from the rocks that's going on. And we inhale a lot. That's because there's uranium and thorium chains that are giving out radon, and the radon gets trapped in a room like this, and you breathe it, and it's unfortunately, mostly alpha particles, which means it mostly stays in your lungs. That's why you get lung cancer for it. That's why you want to have your house and your office ventilated reasonably well. And in your own body, there's also radiation, and I'll get to that in a second. The total is about 3 millisieverts, and so cosmic rays are only 10% of it. So whoops, I got to do more careful calculations than I did. So here are the backgrounds again in a different way. And the radon, in terms of radiation dose to you, is huge. That's why you vent. You make sure your buildings and stuff are well vented. Okay, the thorium and uranium lines, they're only about 4%. The cosmic rays, 11%, terrestrial 7%. The radon 220, as opposed to 222, is about 5%. Those are the sources of radiation that exist. If you want to, you've got to protect stored stuff from that in a certain sense. And so here's a big one, because when I first did the calculations, I thought we could do about a factor 10 better than we can unless we figure out how to solve this problem. You're hot, and you're radioactive. Right, honey? And so it's an issue that you're radioactive because the primary radioactivity in humans is calcium-40, which has a lifetime of about 1.2 billion years, and it's only 1/100% of the calcium in your body. Your body cells use calcium very, very much because it's a conduit to signal and do other things. Okay, so that means if you're a 70-kilogram person, you're having about 5,000 becquerels, which means you have about 5,000 decays a second in you. That is, in the time it took me to say the sentence, you had more than 10,000 decays in your own body. Now, fortunately, most of those decays don't do damage to the person who's sitting next to you. It's the ones that give out the gamma rays and so forth. But the carbon-14, which you're breathing in all the time, eating in all the time, you're ingesting it in various ways. Carbon-14 gives you 3,000 decays a second. Fortunately, it's almost all beta rays, and they do simpler damage to the body. So they're sieverts, or a magnitude less than you would have thought in comparison. Okay, so you got rubidium, you got tritium. These are mostly from the nuclear tests done by the U.S., well, the Soviet Union, the U.S., and China, and that's residual in the atmosphere, but it's the kind of thing. And that's the kind of thing. So it's a potassium-40, but here's an interesting picture in beta rays. Do you recognize what this is? It's a banana, okay? If you eat a banana, it's 1% of your daily dose of radiation. Okay, this is a pork chop. This is, I think, some citrus, some various things like that. Almost everything that you ingest is radioactive. Okay? So it's hard to get away from that. You've got to think about how to carefully choose your cells so you can minimize that potassium-40 decay in them. And I've been trying to work on that. There are ways to do it, but it all seems hard compared to the invention on the other side that Nora and I have done. Okay, so radiation damages cryopreserved cells. And I searched through the literature for a long time till I finally found one article that dealt with this. All the articles that exist deal with in vivo radiation exposure, except this one. Right? I mean, I searched through a lot of literature. I actually had a colleague because I was out of town, use the university, special system to do extra searches. And this is the only one that I found. And this is just shows you what kind of radiation you got to worry about. Okay, here's what they found. It's not a perfect article, but at least there's some data. So these French people did exposure to cryopreserved cells at 2 months, 5 months, and 7 months. Not very long time, but whatever it is. But they did it in an interesting situation. Level 1 was at their lab in France. It was below a 6-story building, and it was 2 more stories underground and a low radiation environment and low radiation equipment. The radiation background was about 10% of what you get here at here near sea level, right? And this is how many cells came out, roughly 7% plus or minus 2, that came out looking damaged after the 7 months of now, they also then went to Grenoble, to the top of a building, and they took the stuff and exposed it on top of sandbags that had some thorium and other stuff in it. So the cosmic rays were higher, and the gamma rays from the thorium were higher. So they got roughly 10 times the dose, okay? And you will notice they got up to about 16% of the cells being affected so badly they died. Right? Doesn't mean that some others weren't affected, it just means that. And then they went to Campview and I is one of our favorite places, deep underground. There's a deep underground facility which has lots of shielding, uses low radioactivity metals in containers, and has it's called uranium. It's a cement that's radiation shielding. It's made out of special material, and so they got to a dose which is way under the 10%. It's less than 1%. It's probably about 0.1% of what it would be, and they got this kind of range for the answer. Now, there's lots of things about this paper that I don't think is perfect, but this is the only data we have. Okay, and it kind of is in the right range for my calculations, but it isn't perfect for what we want to know. We'd like to know for longer term. If you did for longer time periods, the effect would become more dramatic. And if you control things a little bit, they're using approaches that aren't, pretty much okay. But at least they went to a somewhat protected area, to 10-meter water equivalent, and higher up in the mountains, a kilometer up. So they got, 3 times as much cosmic rays. And then they put sandbags with thorium gamma ray producers in it and put the stuff on top of those, so it was getting the stuff from both sides. And there was an effect. Now the question is, how good is this result? When you read the paper, it's a little terse, a little complicated to read, but it seems like they did reasonable stuff, but you'd like to have more stuff, and you would like to have a procedure that didn't have all these extra deaths, right? Because this guy could be way down to here if it wasn't for the other things that are causing the cells to die. All right, so this is an issue. Now, that caused me to do 2 things. Let me say that. Let me go back and say that, and then I'll try and get this. If you look at this, the Earth has a magnetic field. That Earth's magnetic field turns high-energy cosmic rays around and sends them back, but not high enough, pretty high-energy ones. So if you look at the place at the North Pole, the South Pole, magnetic poles, you get a lot of radiation coming in. If you look along the magnetic equator, it's much less. The minimum, because it's slightly offset from the center of the Earth and everything, the minimum happens to be in southern India and Thailand. So it means if you're flying your samples into Thailand, all this kind of stuff, you have lower background radiation coming into your samples, even that short-term handling, and you do that kind of stuff. Now, one of the things that I was advising with this group that's trying to make the big center like this in whatever it is, and it has funding from a big group that is both charity and linking, and a Chinese company and the Royal Thai family to build one of these at the Royal Thai Hospital. I wanted to put it in the Karsh Mountains because the Karsh Mountains are made of limestone, which is very low radioactivity. You can put a shield into it easily if you can find out how to solve the potassium 40 problem. And you are 2 hours away from the doctors. So you can get the stuff back and forth without much damage, right? But the doctors aren't going to be bugging you and telling you this is how you should do it. You're going to do it to make a really effective center. So that's one of the places. And as I say, that was very far along. Then, but there were still arguments going on. Then Chinese Lunar New Year came in. That slowed everything down. It's starting up again, but it looks as though there will be a very large center like this put in Thailand, and the money and the government and so forth, everybody's behind it, as we can see. Now, the other place that I've been talking to about doing this is Mexico. Now, it's not because Mexico is so advanced that way, but Mexico City is at 2.2, 2.3 kilometers. Okay, that's higher than these guys, right? You expect the radiation dose to be at least 3 times as high, even if you take a little care. So you have to come out with that. And so I pitched this idea a little bit to a university, and instead, one of the people that I've known for a long time working, he rushed and talked to his rich friends and benefactors. And one of the guys owns a gold and silver mine, and he wanted to put the storage facility in his gold and silver mine. Well, there's parts they've mined out, so you can do that. But a lot of, I don't know this particular mine, but a lot of the mines in Mexico are highly radioactive. You've got to vent them to get the radon out. You've got to do a bunch of other stuff. And so it's not super cheap to do that. I, for various reasons, I believe in a horizontal access rather than a vertical access into stuff. But anyway, they're working on that. There's a number of people on other. So investors want to be in this, and we put a proposal in to the Mexican NSF to try and get this. So the expectation is we'll be doing a study and we'll be doing that because there are enough rich people in Mexico City. They will pay to store their stem cells and their T cells, even if the average population doesn't get it. In Mexico City is 20 or 40 million, depending on how you draw the box around it. There's a big set of people to do that. And it would be good for Mexico to have stem cells that were robustly made and cheap so that more of the population can afford it. So we're making progress there more so than I like because it's being driven by the financial people. People want to make a bunch of money from it more than by the scientists, but we'll see what happens. Okay, so if you think about what has to happen, you got to think about designing it as an engineering production design problem with some scientific questions that need to be fixed, right? We need a couple of physicists working on it, a couple of chemists, some a few bioscience guys, but mostly engineers, because this is a production engineering design problem. How do you set the thing up so that as time goes on, you can automate it more and more until you're really the Dell computer of stem cell processing. And that's a thing. Now the problem is, since we're putting stuff in people, there are going to be regulatory compliances to prove that you're monitoring this whole process and that you're putting quality products into people. And that, I think, is a good thing to do, but it requires extra over the normal building products kind of device. Okay, so this is the slide that I said for conclusions in the beginning at the talk that I gave in Thailand late last year. So there's some Thai phrases. It turned out most of the people weren't speaking Thai, so it was a waste. But here's my conclusion. We have some research and some design to be done, that a university is the real place to do it. And we just have to think, how do you put together a team that can make that? And I predict a good fraction of people in this room are going to want to use the stem cell therapy for something. Right? But it's great also that it gives you a job, it gives you a reason to keep being here. So thank you.
Well, thank you, George, for the interesting talk. So now it's time for some questions.
It was so clear.
Mm-hmm. Okay.
So you spend a very meticulous way to shield the stem cells from radiation, like put in the mountains and so on. While our body is actually subject to much worse radiation. So, and their current technologies of storing stem cells, like they're probably not very good compared to yours. Are there evidence to show that the stem cell will be damaged over the course of 100 years by radiation?
Well, we apparently don't have any life sciences people. So if you look at what goes on in human cells, as opposed to viruses, in human cells, we have double-stranded DNA. That's not an accident. Cosmic rays break single-stranded DNA. If you're going to preserve, so a human, for its longevity, depends on preserving its DNA information and preserving the functionality in the cell, which is the nucleus telling the RNA what proteins to make. And those errors build up in that, and you get a lot of bad proteins sometimes. And the mitochondria producing, and they have to produce a lot of ionized radicals, which also can damage the zone. So you have to use them in a careful way. Those will get damaged by cosmic rays. And that is one of the reasons that people age, but the body, when it's alive as opposed to frozen, the body has a lot of repair mechanisms. So if you look at what DNA does, it should have more errors than it has. The reason that it doesn't is there are machines, little machines of the body, that go by and scan up and read the DNA up and down and fix some of the errors. And so when we talk about the Hayflick limit and the telomeres and so forth, it is the body is tuning itself to try and make it so it doesn't have to kill cells and grow new cells, because every time it divides, it builds up errors. It's trying to take and keep those cells in as good a shape as it can during whatever's going on. But eventually, errors build up. And a lot of those errors come from radiation. All of those errors come from other bad things in the environment. And it's even more complicated than that. If you look, as I mentioned, for a lot of cancers, it goes as the sixth power of your age, internal cancers. Why does it do that? Well, it means there are 7 things that are low probability. So if the first one is probability 1 times your age, it's P times T, P1 times T, P2 times T, all to P7, but you don't need a times T, because as soon as you get the other 6 plus that 7th, you get cancer. That's why some people that have genetic disposition towards cancers don't get it, and some people do. It's a stochastic process whether you get those 6 or 7 things you need. There's a second factor, which I was mentioning. Your T cells lose their potency at a rate of half per 16 years on average. So that as you get older, your immune system drops down. So young children have a different issue, but compared to what you would be at a young child, when you're 16, you're half, you're a quarter at 32. By the time you get to 64, you're getting pretty down on the immune curve. That's why when a virus comes along, like pneumonia or COVID, old people die at a much greater rate than young people, right? And it's because they are less able to do it. So the answer is the body has some mechanisms when you're alive and the chemical is working to try and fix your cells up in case there are some damages. And so there's long been an argument about, as radiation dose goes down, does it go down linearly or does it dip and come back up? There's different, and we still haven't known for sure. There are some things that seem to do that, some things that don't. And so that's what I should be addressing in the next lecture, but it would be too complicated to do everything in the next lecture, but we'll see. So the next lecture is, essentially your digital twin, where you model yourself and you see what's going on. But you can see that your body does fix some things. It doesn't fix everything. It fixes some things. And if you treat your body carefully and put it in a good environment and everything, it manages to fix a lot, but it won't last forever, right? If you want it to last a lot longer, I got upset when I was asked to do a third talk or whatever it was, said ciao, and then the people weren't paying attention. They were rustling their papers and reading their phones, and I said, you're all going to die, right? And people looked up from their phones and everything. And I said, you didn't actually have to die. If people haven't gotten satisfied with the fact that we're gaining about 2 years per decade every year in life expectancy, but in fact kept rising it up, kept doing these kind of things and raising it up, like giving yourself a stem therapy boost when you're in your 40s and early 50s, you could rejuvenate a lot of part of the body to make the lifetime much longer. And if you're gaining instead of gaining 2 years per decade, you gain more than 10 years per decade that you live. How long do you live? Well, let's see. I finished this decade and I got 10 more years. I finished the next decade and I got 20 more years. I finished the next. Yeah, it's how much can you fix people up? You can't fix people up unless you can do the the DNA and protein system analysis in human beings carefully and go in there and correct those. And so pretty much everybody in this room is going to die. But had we been more sensible about things, a lot of people in this room wouldn't have to die until they wanted to. You could be rejuvenating yourself for hundreds of years. And so, but you have to fight it. You have to have stored your original DNA or close to your early DNA to be able to keep fixing your cells. That's a really long-term problem. That's why the university gets the last past 20 years.
Okay. So any other question?
Hi. So when I was born in 1989 in Italy, there was no possibility of donating the stem cells. But when my brother was born in 1996, my mom donated like the umbilical cord, like the pipe that comes out of the belly. And it was kind of a new thing. I wonder if there is like any country that is more advanced in donation, and what is the best way to donate stem cell?
Right. So it used to be that Singapore and Hungary were more advanced because they were doing it for all their citizens. And in fact, it's one of your national treasures because it's your identity. Everything about all your citizens, is in the DNA and all the data you collected, you and the companies have collected about them. And you want to preserve that very well. Now the problem is, I claim we're not quite preserving them nearly as well as we should be. But if we engineer the process and we do some of the scientific research to fix some of the stuff, we will be able to keep them from a long time period. And so the answer is, in most countries, only if you're wealthy enough to pay someone to store the cells is there a system to do it. Now, you saw that ad. Hong Kong has it. Hong Kong, rich people have been paying to have their stem cells, their children's stem cells, put on ice, right? Put on liquid nitrogen. Now, my argument is they didn't think about protecting them from radiation. And my belief, which is his thing, my belief is that frozen cells are much more susceptible to damage than in vivo cells because the in vivo cells can fix some of the damage. So the answer is yes, everybody should have, and yes, you should be thinking about storing your T cells, right? But you want to go to a company that's going to store them in the right place, the right way.
Okay.
And my colleague in Mexico that followed my advice and had his child's stem cells, frozen, paid for it. Turns out that the place is at 1.2 or 1.1 kilometers height, so not as bad as Mexico City, but still not good, right? And you don't know whether those, you want to have your radiation measuring equipment check those tanks to make sure they're low radiation. Yeah, CanView knows this well, in principle.
Okay. All right. So if there's no more questions, so let's just thank George again.